proportion. You have a lot of new terms being used. You talk about business analytics, artificial intelligence, you talk about data science, you talk about big data. All these things suddenly became famous. And in the last 7 or 8 years, it has been growing in a very steep manner. And that doesn't seem to be any stop as far as the growth is concerned. Maybe it will taper off after a while, long while. So let me start this word analytics and statistics. The father of statistics, Ronald Fisher, is a legendary statistician, is no more. 1890, 1962 is the lifespan. And his only doctoral student is the pride of India, Dr. C.R. Rao, the founder director of Indian Statistical Institute, who is turning 100 years this year, the living legend, the only doctoral student of Fisher. C.R. Rao wrote a beautiful book in the year 1948 called Advanced Statistics in Biometric Research. There Fisher wrote these great lines. It's not a foreword, but he wrote these great lines. And let me just explain this as a starting point or a launching pad in the context of predicting corporate bankruptcy or insolvency. A statistician is no longer an alchemist expected to produce gold from any worthless materials offered him. In other words, we all talk about data and we say we can do everything with data. But then the word of caution, it depends on the material that is given. So the statistician is like a chemist trying to gauge how much value the data set contains and also capable of extracting this amount only, nothing more, nothing less. For example, if the data set has 60% value and 40% worthless things, a statistician should be able to extract all the 60% if he is competent. He should not extract less than that, but he cannot make it 100%. And therefore, under these circumstances, it is foolish to commend a statistician because his results are precise, or condemn the statistician because the results are false. The statistician is only to produce what the material contains, the value of the data. In other words, you should be like an Annapakshi, the divine swan in the Manasarovar, which is capable of extracting a mixture which contains milk and water together, extract and derive and separate only milk and drink that. Milk is separated from water and the Annapakshi drinks the milk. The analytic professional today should be like the Annapakshi, the divine swan, from the data set, derive insights and leverage on them for decision making, and just throw away the worthless materials that it may contain. The value of the data set, which will give insights, is paramount, and that is the context in which the analytics role looms large. And Fisher said this in 1948 in those 4 or 5 lines which I have presented to you. They look profound and it has stood the test of time even today. And therefore, your capability must be to extract insights, derive insights from data. All the insights that data set could give you, you should be competent enough to derive. And that is the launching pad. Analytics is not only statistics, but statistics I would consider is the heart of analytics, and it's an important component for decision making. So in the modern world, the quotation of Fisher, which I have presented to you, is very profound and it is true. We all say "Gee go," a standard expression, garbage in, garbage out. But to me, it is not interesting. Look at Fisher, the way he has put this whole idea, deriving insights. So that is the purpose. Predicting something will happen only if you are able to understand pattern and derive insights. And then comes here, there are three important terms that are used in analytics: data science, machine learning, artificial intelligence. Data science deals with the ability of the person to extract insights from data following models, methods, algorithms, whatever you can think of, and perhaps driven more towards deriving insights. Machine learning is predicting something. What would happen if this is the case? Will the customer default on a loan? Will a customer buy my product? Is my product appealing or not? You want to predict something. The target variable could be a number or a group variable which you would like to predict. Then comes artificial intelligence, is automation, implementation of the decision, and completely automated. And therefore, you say in Great Learning also, a course on artificial intelligence and machine learning, if you make it AI ML and add another A, AIM law, it becomes artificial intelligence and machine learning algorithms. So data science, machine learning, artificial intelligence, these are the three terms I have broadly explained what each one does. And all the three terms are useful in predictive analytics, predicting something, because you can't predict something in vacuum. You will have to have the understanding of all of them, which are all embedded in predictive modeling. Then comes pillars of analytics, which all of you know: descriptive analytics, diagnostic analytics, predictive analytics, and prescriptive analytics. So descriptive analytics deals with summary of data, the measures of statistical averages, central tendency, dispersion, standard deviation, range, all kinds of measures, and then visuals such as histogram, box plot, graphics, trend analysis, tracking analysis, graphs, and pivot tables, charts, all those things, including dashboard. Then diagnostic analytics tells you what happens, why the data is behaving like this. Descriptive analytics tells you, can you write a story with the numbers that you have got or the data that you have got? Diagnostic tells you why the data behaves like this. What are the reasons? And that is diagnostic analytics. It deals with the hypothesis, it deals with uncertainty, it deals with the bell curve, and you are able to formulate some hypothesis, prove or disprove, but your aim is to find out the cause, what causes the effect, and diagnostic analytics is important. Then predictive analytics you are using to predict something. What will happen if this data behaves like this? Can I use this data to predict whether the customer will default on a loan? Can I use the data to predict what will be the demand for a new product that I'm going to produce? All kinds of things which are happening, that is predictive analytics. Prescriptive analytics tells you, now what should I do? You are talking about descriptive, diagnostic, making it too technical. What should I do? Prescriptive analytics is something like a doctor prescribing medicine, what you should do. This is what you should do. You are suffering from fever. Fever is a symptom, but actually the fever is due to typhoid. Unless you take medicine for typhoid, the fever will not go. Today, as you see, paradoxically, nobody is able to prescribe. We are in an extraordinarily turbulent oriented time, disruptive time, where the COVID-19 is impacting all of us, and the world is yet to find something as a medicine which they can prescribe. So prescriptive analytics is similar to that. Descriptive, diagnostic, predictive, and prescriptive. You don't have to always go in this order. You can directly go from descriptive to prescriptive. It depends on the nature of the problem. Otherwise, you will have to explore data, do some descriptive, find out some reasons, patterns, then predict, then give prescription. This is how this whole thing goes. Then another vocabulary which we will have to understand is supervised learning, unsupervised learning. Two parts are there. In a supervised learning environment, we have a clear definition of the dependent variable and the host of predictor variables. Meaning, I want to know the target. I know the target, but I want to predict the target. The target becomes the dependent variable. And the target is related to a number of variables called the predictor variables. And statistics, they use the word independent variables. Here, I try to avoid the term because people will think all the variables are independent, means they are uncorrelated. The correlation between them is zero. No, they are not statistically independent. They are called, unfortunately, by the term independent variables. So I'm using predictor variables. Dependent variable, which depends on the predictor variables. Dependent variable could be called a target variable. And therefore, given the inputs, can I predict the output? So in the computer parlance, you can say input, process, output. I want to predict the output based on the input, but there is a process, methodology, model by which I do the whole thing, then I predict. This is the supervised learning. In the unsupervised learning, I cannot have the luxury, I do not have the luxury of the dependent and independent variable. I simply have data. I have no idea. And therefore, you will have to find out the output in terms of the pattern that is emanating from the data, the pattern, trends, associations, which I leverage, and then I try to find out whether I can do something called the outcome. And in today's environment, very often we go from unsupervised environment to the supervised environments. So let me say unsupervised, one example I can think of is clustering. You have data, you want to find out the pattern. Can I just divide them into few clusters so that there is similarity within a group and variability between the groups? So in the parlance of analytics, we say homogeneity within a cluster and heterogeneity between clusters. The moment I do that, then I have identified 3 clusters. Now I should predict. For predicting, I need supervised learning. And therefore, from clustering, I can do a supervised learning to predict the outcome or predict the object to which cluster it belongs to. Supervised learning examples, all of you know. You have, for example, multiple regression, logistic regression, discriminant analysis, support vector mission. All these models and methods, they have a very clear definition of y is a function of x. Given x, I want to predict y. Unsupervised learning, you have examples of clustering, principal component analysis to reduce variables into underlying dimensions, and then association rules are what's called the market basket analysis. These are examples of unsupervised learning where my aim is to identify pattern. And therefore, it's not necessary always I have an environment of supervised machine learning where everything is clearly defined. You may have to discover pattern, and that's where the unsupervised learning comes. Now, today's topic, we are talking about how to predict corporate insolvency or bankruptcy using financial ratios. So we have input variables or predictor variables or financial ratios, and I need to predict the Y, which is whether the organization will become insolvent or solvent. Will it be healthy? What is it? I want to predict. And therefore, it falls into the scope of supervised learning. So let me just begin this part with an example. today we are going to talk about linear discriminant analysis discovered by Ronald Fisher in 1936. You may be knowing several faculty members, professors, they use this supervised learning or unsupervised learning, whatever, the iris data, the famous Anderson's data, where the sepal length, sepal width, length, petal width, they are all given as predictor variables, and you will have to classify them into setosa, versicolor, virginica flowers, the famous iris data everybody is using. But Fisher was the first to do the two-group discriminant analysis in the context of taxonomy. He wrote a classic paper. And that was further improved by C.R. Rao, Mahalanobis, Paul Green, and Morrison in a number of ways. I am standing on the shoulders of the greatest gurus. And in all humility, I must say, I've learned a lot, but they are like Himalayas. I'm only trying to get a part of it to share with you. And you know very well that logistic regression is more popular in the analytics world than discriminant analysis. Here, discriminant analysis of Fisher, but you will discover in the recent times for pattern recognition, dimensionality reduction, feature selection, discriminant is bouncing back alongside support vector missions. These are the scoring models. And therefore, I'm picking up this, and particularly its application in the financial side, banking side, predicting something when the predictor variables are continuous, a remarkable technique. And it also has the advantage of multi-class, where it can perhaps outperform even logistic regression, because the multi-class in logistic is a lot harder, and discriminant using the Fisher's approach and Mahalanobis classification, we will be able to do multi-class. So what is this word discriminant analysis? Discriminant, if you use the word, is viveka in Sanskrit. Differentiation, the ability to discriminate. That's what is discriminant. Now, the idea is, can I separate 2 or 3 groups in the sharpest manner possible? Is it possible? If so, how do I do that? That is the question that is asked. Some examples let me give you. Do heavy users and light users, which is there, differ in some other characteristics as far as the use of our product is concerned? Do you have a case where I can differentiate, for example, bankrupt companies from solvent companies in terms of the financial ratios? Can I differentiate the loyal and non-loyal customers in terms of their perception toward brand, toward shopping, and other attitudes? So I can use discriminant analysis. So the idea is separating groups in the largest possible distance possible. So differentiation is the hallmark of discriminant analysis. So how do we achieve the largest separation between groups? That is the goal, singular goal. The singular important feature is differentiation. So far, I hope it's clear, and any query you can have, I'm making it as simple as possible. I hope things are clear to all of you. They are very simple concepts which we are doing. So differentiation. What are the goals? 3 goals of discriminant analysis: profiling, differentiation, classification. In fact, you can put these 3 goals as goals of analytics itself. How do you profile? How do you differentiate? How do you classify? The classification part is the predictive analytics part. Using the training data, test data, you do that. So profiling, differentiation, classification are the 3 goals of discriminant. Where do you apply? I have taken my own life experience, and few of them I'm highlighting here. The application of discriminant analysis. Why do you say discriminant is very, very important? So let me project it in a big way, the application part. In a textile mill, the quality of the cotton depends on the chemical characteristics. Linear discriminant can create a score. And if the score of the sample is more than the cutoff point score, the threshold score, and that you call this as the discriminant analysis, that if the score is more than the cutoff point score, the cotton quality is good, else bad. In sanctioning loan, a bank can use financial indicators and develop a score. If the score is more than a threshold point, classify the customer as a defaulter, else a non-defaulter. In the MBA admission, for example, based on the grade point average, the GMAT score, and the performance score in the interview, whether to admit a candidate or not, you can even add one more waitlisted. If the score is more, admit. If the score is in a particular range, waitlist. If it is less than the cutoff point, reject. So there are several applications, and that is why the scoring model is a lot easier to implement. You have to simply say, this is a score, if it is more or less. But how do you develop the score? How do you convert them into an equation? And that is where Fisher has evolved some mathematical things, and I will try to make it as easy as possible to you. So don't worry about these expressions, because these days, sometimes the expression could be difficult, but let me make it a very simple maths only I'm doing. There is a Z-score or Z score, where you can see in the equation, this is there A1, X1, A2, X2, A3, X3, AK, XK. Z is a score. X1, X2, XK are all the features or the predictor variables. You can call them features. And A1, A2 and all those terms, they are called the weights of the discriminant equation. Now, how do I get the weights A1, A2, A3? On what basis? Fisher says you compute the mean for Z for the first group, call it Z1 bar. You compute the mean for the second group for all the feature variables, call it Z2 bar. Then the difference between Z1 bar and Z2 bar is maximum, or the square of the difference, Z1 bar minus Z2 bar square is maximum, divided by variance of Z. In other words, the difference is divided by the variance. The squared distances divided by the variance must be maximum. Incidentally, this term is called the Mahalanobis D squared for those who are interested. But primarily, a very simple layman's way, if you have to put, Z1 bar minus Z2 bar must have the maximum distance. How do I achieve? And I have a constraint, variance of Z is set equal to 1. Very simple maths. And packages are there, Python is there. You can even model it in Excel. And Python, I have got something which I will show perhaps in the end if time permits. My aim is to say, if there are two groups, I want to separate them. I compute the mean of Z, which is the Fisher's Z equation, discriminant equation it's called. The mean for the first group and second group based on that. And then I want to maximize that distance subject to the variance of Z is set equal to 1. And that is the separation part Fisher has mastered. In other words, how do I choose the weights A1, A2, AK so that the difference is maximum? This is a simple maths. So let me now come to an example. This computer does the job. You leave it to the mechanical slave called computer. Some skills in Python or coding, you will be able to get it. Now let me just go to the next point here. Is a classic paper of Altman titled Financial Ratios, Discriminant Analysis and Prediction of Corporate Bankruptcy, Edward Altman, a seminal paper, the Journal of Finance in the year 1968, which stays even today relevant. Several research studies have been done. Even we have done some study. Personally, a paper is getting published in the area of predicting financial health of banks in the Journal of Emerging Market Finance. We are inspired. I'm inspired by Fisher. To me, Fisher is the ultimate. There is nothing that Fisher has not touched in statistics. So Altman was the first who wrote a classic paper using the Z score, 589,609, the reference I have given. And I could pick up the data from Morrison's book and entered it in Excel, and then a CSV file I have converted. But I have labeled them as follows. There are 33 companies which are bankrupt, Altman took, 33 companies which are solvent. If you use the word insolvent and solvent, equal sample he has taken, but unequal also is possible. The goal was to see whether the bankrupt firms and solvent firms could be sharply differentiated or separated in terms of the critical financial ratios Altman took. They are WCTA is the acronym I have used, working capital to total assets, retained earnings to total assets, earnings before interest and tax to total assets, which I call it as EBITDA, WCTA, RETA, EBITDA, then market value of equity to the book value of the total debt, which I call it as MVEBVTD, and sales to total assets, SATA. These are the 5 financial ratios Altman used and developed a classic Z equation, the model with the spirit of Ronald Fisher, the discriminant model. Now let me explain briefly the ratios, why the ratios are very, very important. Let me explain that to you. And so that you can see clearly the slides. As you all know, working capital to total assets, WCTA, is a very important measure of net liquid assets. So current assets minus current liabilities will be the working capital. And a firm which is experiencing consistent operating losses, shrinking current assets in relation to the total assets. Therefore, this is very important differentiator according to Altman, and let's see how the model works between the bankrupt firms and the financial, the solvent firms. Okay, then retained earnings to total assets, RETA. Now, organizations which have been in existence for many, many years would have got a lot of accumulated profit. They would have accumulated more, and therefore they are less vulnerable to bankruptcy. Whereas a relatively young firm with a low RETA, because of the relatively young age, is more vulnerable to becoming bankrupt compared to the well-established older firms. And therefore, this is a very important ratio to separate bankrupt companies from the solvent companies. Then earnings before interest and tax to total assets. All of you know, do you have enough money to repay the long-term interest? And therefore, this ratio is very important. Supposing your earning is 20, your interest is 40, you are not doing well, you are in trouble. Therefore, this is a very important ratio. Then the market value of equity to the book value of the total debt is very important. If the market value is 100, your total debt is 10, you are doing well. But if your total debt is 1,000, then you are in trouble. And therefore, these 4 ratios, the last one is sales value to the total assets. Prima facie, at the tip of the iceberg, this may not be very critical because this ratio is unique to other variables in the model. This is also taken Statistically speaking, perhaps this ratio may not be, or maybe the least significant among the discriminating power. So using these 5 ratios, is it possible to develop an Z score and predict the corporate bankruptcy or insolvency? A classic paper of Altman. I have picked up the data, and let me just show you some of the findings, the features. We have used the computer model, and then we have done the exercise. So let me just go one by one and explain this. Profiling. If you look at the group means, it's so obvious the bankrupt and solvent companies are highly separated, at least prima facie. The WCTA for a bankrupt is minus 6.05. These are all ratios. And the solvent one is 41.38. Retained earnings to total assets is minus 62.51 for bankrupt, and solvent is 35.28. EBITDA is also similar. And then market value of equity to the book value of the total debt, that's also showing remarkable separation between the two groups. SATA, as you can see, is not making a very major impact. So the profiling part is done. We have got the group means. Now, some visuals of this when you do, that is visuals, differentiation is the second goal of discriminant analysis. Profiling is the first goal. And then the visuals, when you say, look at the bankrupt companies and the solvent companies, a picture is worth 1,000 words. Now, perhaps here, if not 1,000, at least you can give 500 words or 200 words. But look at the graphic. Bankrupt company is here, and solvent company is way above that. The working capital is doing so well. And then, similarly, you take retained earnings. There's a vast difference between the bankrupt and the solvent company. Then the third one, earnings before interest and tax, similar story. Solvent company is far ahead of the bankrupt companies. And then the market value of equity to the book value of the total debt outstanding, you see that the differentiation is very sharp. The last one, SATA, as we have seen, there is a difference, but it's not substantial. In other words, the ratios point to the fact that it is almost a linear separable case. We must be able to evolve an Z score or a model based on Fisher's method, which Altman has done, and then try to classify and see the accuracy. So let me just focus on that now. And let's see how it goes here. So the equation, as you can see, the Z equation is here in the top, which you cannot miss. Z is equal to 0.153 WCTA plus 0.183 RETA plus 0.0418 EBITDA plus 0.0077 market value of equity to the book value of the total debt outstanding plus 1.2543 SATA. Remember, the Z score is the Fisher score based on the data that is provided, raw data. It is not a standardized model, but that is the beauty of discriminant analysis. It works very well, whether you standardize or not, it works very well. The only care you should take is you should not blindly interpret the weights. It is similar to the regression weights, and therefore you should have a common denominator to know which one is more important. Because if you go by the weight, you will say SATA is very important, but it's not so. Now, this equation of Fisher, once you have got this, we work out the mean for the first group, the mean for the second group, Z1 bar, Z2 bar, and then take a cutoff point score, which is 2.9714 here. So if the score is more than or equal to 2.9714, predict solvent. If the score is less than 2.9714, predicts insolvency or bankrupt. That is the beauty, the cutoff point score method. And just for the sake of clarity, I have put a small part of the data after the prediction, the Z score and prediction. Look at the first one, first company. The Z score is minus 1.7785, which is definitely less than 2.974, and therefore it is bankrupt. Similarly, second one, 1.8231, definitely less than 2.9714, therefore bankrupt. And the third one is minus 4.1433, is also bankrupt. Let's look at some data here. The solvent company is 4.4059, which is more than 2.9714, and therefore solvent. 5.4811 is again more than 2.9714, therefore solvent. 4.4147 is more than 2.97, therefore solvent, etc. In other words, this is the beauty of the model. Develop the Z score, and then once this is more or less, you are able to classify. Now, the answer that I have provided above is in agreement with the software Python, not only that, and also the textbook Morrison, where these coefficients are all there, and therefore the answer is correct. And some books divide the weights by the standard deviation, and our software also gives, but they are all proportional. But this is the correct solution, which is in agreement with the textbook of Morrison. This answer is given there. And Python output, interestingly, is in agreement with Morrison and C.R. Rao. And therefore, I have just put that from the equation. And the only thing the software does is it subtracts the cutoff point from every score and says if the score is negative, it is bankrupt. If the score is positive, it is solvent. So both are same, but I just want to explain the cutoff point score, which is the fundamental and spirit of Fisher. And this way, the model is there. This is the classification part. We have done profiling, then we have done differentiation, we have done classification. Now let us look at the confusion matrix. A beautiful output from Python Seaborn graph, and accuracy 95.45%. 3 firms are wrongly predicted. 63 out of the 66 are correctly predicted. And that is the accuracy. So the so-called sensitivity, specificity, you can work out. It's a fairly simple thing, but I don't want to sound technical. All I'm saying is there are 33 firms in actual which are there, out of which the model has correctly predicted 31. There are 33 firms in solvent, out of which the model has correctly predicted 32. And therefore, the accuracy, 63 out of 66, which is 95.45%. I hope this part so far is clear. Let me finally do a recap, then wait for the question answer. But this part is important, the confusion matrix. The word confusion matrix is sometimes interesting because the model gets confused in predicting. It places some of the right things in the wrong place. Is classification matrix or confusion matrix, you may call it. Then comes here, which variables are important? As I told you earlier, we cannot go by the weight of the discriminant score. They are not as meaningful as the correlation. If you see the weights, I can draw any conclusion, but I look at the correlation. The discriminant score versus the input variable, how much are they correlated? If you see here that SATA, which has a higher weight in the equation, is the lowest here, 5th rank. The most important one is the retained earnings. The next one is the WCTA, working capital total assets. Then the EBITDA, earnings before, is 4th. And second one, if you see the rank, RETA is number 1. Then Market value of equity to the book value of the total debt is number 2. Okay. Then number 3 is working capital total assets ratio. Number 4 is EBITDA. Number 5 is SATA. In other words, we can do a statistical significance using the F ratio or the T test, but I'm not going to do that at this stage. I'm only trying to say the relative importance of individual ratios in terms of achieving the differentiation. The most important is RETA. That's the most important. The second one is market value of equity to the book value of the total debt. Third one is WCTA. Fourth one is EBITDA. All the ratios 1, 2, 3, 4 are close to each other. RETA is dominating, but SATA is low, as you can see. So the separation part. In other words, I do a discrimination, I develop an Z score model, then I compute the cutoff point score, then I classify, then I say which variables are important in the classification. That is the succinct spirit or the quintessence of Fisher's discriminant. Now let me show you here with a little bit of ingenuity. You can say the scores can be converted into a multivariate normal distribution based probability or a posterior probability. Statisticians and the SMDM faculty will use Bayes theorem, and Bayes theorem is applied here and the scores are computed into probability. I have with you in Python, I have been able to develop the receiver operating characteristic curve, which is very important in analytics. If you see the receiver operating characteristic curve, the curve is very, very steep, as you can see here. Very, very steep, and you are able to have 95.55% of area covered under. The x-axis is false positive, the y-axis is true positive. The true positive is the sensitivity, false positive is 1 minus specificity, if those of you who would like to use the term, but I call it true positive as the confidence level and false positive as the power of the curve. How powerful the curve is in differentiating the bankrupt companies from solvent companies. 95.5% area covered, the receiver operating characteristic curve. So this is the discriminant analysis part. Let me quickly go through a kind of a summary. What have we done? We said that analytics is an important thing. We need to remember Fisher, that statistician is not an alchemist who can produce gold out of any material given. We have to be like an Anna Pakshi, separate the insights from the useless things in the data set. And then the terms, data science, artificial intelligence, machine learning, we have explained with examples. Then the pillars of analytics, descriptive, diagnostic, prescriptive, and predictive. Then as part of the supervised learning, which we have explained that demarcation between Y and X is clear, unsupervised, it's not clear. Here is a case, a discriminant analysis is a supervised learning. We develop an Z score, and then based on the financial ratios as an example of Altman's paper, we have said the 3 goals: profiling, differentiation, and classification. So we profile using descriptive measures, then we differentiated using visuals, and then we developed the Fisher's Z equation, the cutoff point score, classification, accuracy, and then finally, to top all, you have the fantastic ROC curve in front of you. And that is these are all the Python output. And that is the succinct way. What is this discriminant analysis as a scoring model? How useful it is to predict corporate bankruptcy. Now, having said all this, we are in the world of analytics. How do we apply this? Altman's paper. I have just written with another co-author who is a colleague of mine in Great Lakes, and we just got this paper accepted and getting published soon. The title of the paper is Predicting Financial Health of Banks Using Machine Learning Algorithms. And the scoring model, the Fisher's model, is the inspiration. Initially, we ran a clustering algorithm to the 16 years data or so on all the banks, private sector, public sector, all. Of course, the time series points, therefore 583 observations are there. We divided 70% training and test data, 30%. We did that exercise. Then we predicted the classification that we got 3 clusters, the moderate performer, best performer, and poor performer. It's a multi-class. And then we predicted how good the model is. And we were able to get a fantastic accuracy. And we have published that paper and a relative importance and all that, where the scoring model, Fisher's discriminant multi-class, became handy, and it worked very well. And I'm not able to show the entire thing to you because it is still in the publishing stage. Of course, it is getting published, it is approved. Once the paper is there, it's a copyright with the journal. But I'm able to just to show you some results here so that you have confidence that this scoring model is remarkable. That is what I would like to show you here. The multi-class, they're using the clustering, moderate, best, or poor. The ratios there are the credit deposit ratio, net interest income to total assets ratio, return on assets, capacity, wrongly written, capital adequacy ratio, tier 1, capital adequacy ratio, tier 2, and liquidity to the total assets ratio, liquid assets to total assets, and the gross non-performing assets to gross advances ratio. Non-performing assets, non-performance assets is very critical, all of you know. And the 583, 408, 70% training data, 30% test data, and this is the classification. For the confusion matrix using Z-score, 95.59% accuracy, and you can see, and the test performance is even better, which is 97.71, and this is done in Python. Now, if you want, it's coming to the closure, I will now wait for the question answer. If some of you interested that Altman's paper, I will just execute it in Python and you can see the output if you want to. Otherwise, I don't want to sound technical. I'm willing to take the questions, and perhaps I can show you the Jupyter note here if you wish to, the Altman's thing, which I have developed a coding. Generally, the sklearn library is handy, but some of them are harder with the literature available. And I have developed this, as you can see. If I run this Python code here, all the files that are to be imported are all here. These are all grammar. And I just put here run all. And I will just show you what all I have taken. As you can see, in the last output is the ROC here. And then I have the confusion matrix, which I have shown you in the PPT. And I have the Fisher's equation, which I have shown you in the PPT. And then the profiling part here, differentiation visuals, the bar charts differentiating both the groups. And this is the profiling which you saw in the between the bankrupt and this, except WCTA, we wrote in the different order, but Python has done it in this order. But overall, this is the same. And ladies and gentlemen, dear friends, I have come to perhaps the concluding part, the epilogue also, that the beauty of the multi-class model of discriminant is it's a lot easier and implementable using the software package, and the spirit of Fisher is intact. and more statistical rigor and analysis is possible, but I want to make it non-technical so that how do we implement this in an organization? And that was my aim. I hope you have found it useful. And let me just now take some questions and perhaps do that here. Hello?
Yes, sir. So now we'll take the questions.
Yeah.
I'll be reading out the questions to you one by one. The first question is by Komal Khullar, and she wants to know about PCA and LDA. And her question is, other than PCA being unsupervised and LDA being supervised, is there any other difference between the two? Do they do the same job of feature extraction, dimensionability reduction, etc.?
Okay. It's a very good question. See, there are two things when you want to classify. The aim of Fisher is the largest separation between the two groups you are doing in the discriminant analysis, where the data you know very well is supervised, that I know the bankrupt companies, solvent companies, I know the financial ratios. Whereas in the principal component analysis, I have a set of variables. I do not know Y and X. From the set of variables which are correlated, I try to extract the most important dimensions in the order of the eigenvalue. In the discriminant analysis also, there is some similarity because Fisher is collapsing two groups into a single equation, and therefore the eigenvalue is here also extracted, but here it has a lot more different in the sense that I know the groups, whereas in the principal components, you do not know. You are identifying pattern, which of the variables form a particular kind of a dimension. So, but there is a similarity that eigenvalue is used. But Fisher's aim is, can I separate groups with the largest possible difference? And therefore, if I got 100 features, let us say, then I want to find out which of those features are very critical in separating the two groups. That will be feature reduction using Fisher. But if I use a principal component, I can reduce the features based on the eigenvalue. And if I am able to say that 3 or 4 of the dimensions are going to be critical, then I need only those 3 or 4, and the rest of them I do not, because they explain 80% of the variation. Here also you use trace and explanation of the variance, but here the variables are direct. There is another interesting thing which you can do, because it's a very good question. I want to spend more time. Initially, you have a large number of variables. You do a principal component, reduce the features, then identify the groups using clustering, then do Fisher's discriminant analysis for those clusters using the principal component variables or the dimensions rather than the original variables. In other words, you can think of it as marrying Fisher's linear discriminant with principal component and do fantastic analysis. In other words, reduce variables into factors or components, reduce object into cluster. Cluster, I want to predict using the principal component. There it becomes supervised learning, use Fisher. I think that's my answer to the question. Hello?
Yes, sir. The next question is by Saktivel V. And he asks how to find importance of each predictable variable with respect to target variable. How do we know that the features have enough data to describe the target variable?
How to find out, read again?
How to find importance of each predictor variable with respect to target variable.
Yeah.
How do we know that the features have enough data to describe the target variable?
Okay. See, we have the discriminant score and we have the input data on each of the variables. So we compute the Pearsonian correlation between the discriminant score and each of the input variable data. And the Pearsonian correlation, we can test it statistically if we want, and that will throw light on the relative importance of each variable on the target group, which variable is capable of separating them, the target group. And then what we have to do also is some of them which are not significant, I can remove it from the model and have less number of features. In other words, features are nothing but predictor variables. Suppose I have 100 predictor variables and I work out the correlation between the discriminant score and the 100 predictor variables using the Pearsonian correlation. Then I try to find out which of them are most critical by the significance test. Let's say out of the 120 are most important. Then I do that. The other method is to convert them into probability and try to see which are low probability. Some variables if I add, it only improves the probability of classification marginally. I don't need them. So I remove that. Is it okay?
Yes, sir. The next question.
You can also follow stepwise discriminant to find out the optimal number of variables. That's also possible.
Yes, sir. So the next question is by Hena Bhatt. And her question is, can we use these 5 ratios to predict banks with high probability of bankruptcy or possibility of cooked up books, like in the cases of Yes Bank or PNB?
Yeah. So there's a very interesting question, very delicate question. I'll have to give a diplomatic answer, but I will do so. The bank classification which we have done, the multi-class which I showed you in the end, actually is a case in hand where we predicted these are the banks which are good banks classification, and these are the banks which are moderately healthy. These are the banks which are poor financial health. What happens here is then we compared it with the CRISIL rating, the agency's rating. Then sometimes some of the banks which are rather moderate or poor, they were also given some AAA and high rating, because from the retailer depositors angle, we were surprised that the methodology needs a rethinking. It's possible that some of the banks perhaps have some lobby and influence. They have got some good rating, but we have to really be guarded on this. But the methodology, the scoring model will help you to really find out where does each bank stand in terms of the non-performing assets and the financial health, because 70% of the non-performing asset is due to credit risk. So we have to attack that and find out, probe more. But this model can pave way and say, these are the good banks. So if you compare the prediction given here vis-a-vis the CRISIL rating, if you find differences, you will have to perhaps change the methodology followed by the government to correctly assess the performance.
The next question is by Priyanshu Soni. It is, how do you decide the cutoff point score?
Yeah, the cutoff point score is the midpoint score. So let me just show you here in the Excel sheet. It's good that you asked that. 1 minute. What I have done here, somebody who is able to project it there, let me just show you. The Fisher's equation is here. Bankrupt group, what is the mean? Solvent group, what is the mean, is also here. So in this equation, I substitute the mean scores here for each one of them and then work out Z1 bar. In other words, the Z1 bar is nothing but 0.0153 into 6 point this, 0.0183 into minus 62, etc. and then add it. Similarly, I work out the Z2 bar, the mean score, taking the mean of each, and this I take the midpoint, the sum of all the addition of these two, which is the cutoff point. If I don't take the midpoint, the classification will be, if the score is less than minus 0.37, it is bankrupt. If it is greater than or equal to 6.31, it is solvent. But then what will happen if it is in between? The question will come, and therefore this is recommended by Malnobe's midpoint, which is the addition of the 2.97, the cutoff point score. And that is nothing but the Z score evaluated at the group centroid. Is it clear? Yeah.
Yes, sir. So the next question is by Shrikala. Why do high growth companies tend to have smaller debt ratio when compared to companies with fewer growth options?
Why do, again?
Why do high growth companies tend to have smaller debt ratio as compared to companies with few growth options?
See that the high growth, again, financially, you will have to evaluate. Sometimes due to inflation, you may have high growth. That doesn't mean anything. That is one part. The second one is in terms of the capital structure, the Modigliani-Miller approach, that the valuation of the firm is invariant to the capital structure. It has nothing to do with the capital structure, and therefore it is possible the other way also. So high growth and low growth, in terms of the valuation, if you see, the valuation of the firm is invariant to the capital structure or the debt equity ratio, and therefore we'll have to go deep into that. And the financial ratios suggested by Altman alone, they are not sufficient. We have a number of other ratios, particularly in the bank, the credit deposit ratio, the capital adequacy ratio, and the liquid asset to total assets ratio, the gross non-performing assets ratio. All these are very critical, and we have to add all of them, then build a model. That's exactly what we have done in our paper. Yeah. Hello?
Yes, sir. So the next question is by Mayur Kriplani, and his question is, does this model take into account cash flow and ballooning effect that happens in the case of shell assets?
No, I do not have a clear answer for that, but the explanation of Altman is that 33 bankrupt and 33 solvent companies' financial ratios he has taken. But this question, honestly, I do not have a very clear answer for this to say that but I would assume that when you take the profit and the bankruptcy, the cash loss will be there, and therefore the depreciation, other things, non-cash items are added. But the methodology part, this is much is there, the original paper. So the ballooning effect, I don't have a very immediate answer, honestly speaking. Let me look into that. Hello?
Yes, sir. So we'll have two more questions.
Yeah.
The next question is by Rit Chakraborty. He asks, sir, have you taken the data of the companies in the year in which the companies got bankrupt? How early the model can predict about the bankruptcy of a company?
Here, the Altman's data is a very specific period. It has been very clearly explained. So the bankrupt and solvent companies are put at the same time period. What we have done, something like panel data, 16 years data for the banks over the financial ratios, 7 or 8 financial ratios. We did the clustering, and then we compared year-wise performance also, and finally arrived at the classification. And therefore, the time point is very relevant. We cannot just like that do some model ignoring the time point. The past may not shape the future, but we will have to understand the past. So we can do a panel regression. In other words, 2001, compare all the firms, 2002, 2003, in that way 2016, and then take the aggregation. Because it can be a substantial difference may occur if the time series shows a different pattern. You'll have to understand. For example, right now, we all say GDP, everything is going to be there in extraordinary situation. Supposing we take only this part, you'll have to compare before COVID, after COVID, isn't it? So that part will be there.
Right, sir. So the next question and the last question of this session is asked by Gayatri Doreswamy. And she asks, which journal is the new paper getting published and what's the article title?
Yeah, Journal of Emerging Market Finance, the SAGE journal. And the title of the paper is Predicting Financial Health of Banks Using Machine Learning Algorithms. That's the title. P.K. Viswanathan, Suresh Srinivasan, Hariharan, 3 authors. I'm the first author. I've just shown that slide, the classification. We will not be able to provide more because the journal, it will get published and then one can read.
With this, we conclude the session. Sir, we thank you a lot for giving us your valuable time and explaining such an important topic with so many examples and such extent. I request all the learners to visit the GLA, Great Learning Academy website after this session to take benefit of all the courses, take certificates, and career guidance.
Yeah.
Thank you.
And overall, how did it go? You are happy?
So in my opinion, the learners will be very happy and the learners will actually benefit a lot with the topic that you touched upon today.
The screen show, was it all right sharing the slides? They were all clear?
Yes, sir.
Okay.
Thank you.
Thank you.